This is getting recorded. Okay, it's getting recorded now. Okay, so quick overview again. 3D representations for neural networks, the ways you can use them, the pros and cons of each representation, and then we go on to 2D to 3D style transfer using something called differentiable renders. First up are the different types of 3D representations you can use for neural networks. So there are a variety of them, but majorly these would be the different ways. There is Rgb image data, construction from multi-view Rgb image sets, boxes, point clouds, and meshes. So you can cluster these two representations in two different ways. The first would be, and they may fall into two groups, which are rasterized and geometric forms. Rasterized forms include anything with a rectangular grid, voxels, multi-view, RGBD images. Rasterized forms are usually widely used because they can be easily processed by a CNN. And what we mean by a rasterized form is basically the image represented as a dot matrix data structure that generally represents a rectangular grid of pixels. Geometric forms are anything that can be represented as an irregular grid. So CNN is a convolutional neural network, the basic architecture that is running your machine learning networks. Geometric forms are anything that can represent the 3D shape in an irregular grid. So this includes something that is called the point cloud, or polygon meshes, or simply a set of primitives. Geometric forms usually require some modification to be integrated into the neural network. For example, in the case of point clouds, the machine learning framework that you use should be invariant to the order of points. Otherwise, that would be an issue. And there are pros and cons associated with each representation. So first up, we have RGBD. Wait, give me a second. Okay. So first up, we have RGBD data, or 2.5D data, which is basically your normal 2D images, which has 3 color channels, red, blue, and green. And there is an extra 4th channel called D, which is a depth map, where every pixel has a depth value associated to it. So RGB data is nice because you can directly use convolutional neural networks, which operate on normal images, can directly operate on these. All you need to do is include an technically, all you need to do is include an extra channel which also processes this depth information. Alternatively, you can work on the RGB image information in the image and process the depth data separately. So, as an example of how this is used, the images you see here are one of the ways that you can use this data information. So using depth map, so we did 2D to 2D style transfer. So in this case, you're doing something similar. Instead of style image is the depth map itself, where a depth map is basically a 2D matrix containing depth value associated with each of these pixels. So in this example, a neural network is basically trying to estimate depth for each pixel, and then you can use this to you can superimpose this depth rendering onto any content input image to stylize and basically perform style transfer so that you can get a render texture. Another way that you can use 2D RGBD images is you basically you can edit the depth map itself. So using black and white fractal silhouette. Okay, so excuse me about this part because I am reusing slides which were presented previously. But basically, what we do in this experiment is basically extrude parts of the depth map away, and this basically lets us manipulate what the depth map affects. Okay, are we going to share this slide deck? Yes, I can share these slides for you to view at a later point. So the downside of an RGB image is basically it doesn't give you a full 3D representation. Since all you're looking at is a image from a set perspective and a set of depth values associated with each of the pixels in an image, it becomes difficult to give a full 3D representation. While we can use multiple RGB images to reconstruct a full 3D image, which we do in the case of, say, multi-view reconstruction framework, we run into a number of issues, technical issues, which don't let you get a that basically cause problems when you're trying to do the full reconstruction in itself. So move on forward. What we can do is, instead of simply using a single RGBD image, what you do is 3D reconstruction from multiple images. So this is the reverse process of basically obtaining, it is reverse process of obtaining 2D images from 3D scenes. In this case, what you take multi-view RGB images, data, which is nice because, again, convolutional neural networks can directly work on them without any modification at all. One of the previous semester's projects used a multi-view set to basically do 3D reconstruction. So in this project approach, they used multi-view reconstruction to build sections. So the approach used by this thesis work group was to use building sections to extrude and generate models. So what they do was they cut the model into simple sections along different viewing axes. Then they use this image to perform style transfer on these sections. And due to irregularities and differences between how the style was transferred in adjacent sections, they had to extract and trace a main feature across multiple style transferred images. The key idea was that the students needed to choose specific style features that persisted across multiple building sections. And then they thresholded these features to perform an extrusion and combine them all together to get a final 3D spatialized style transferred model, which, well, when you see on the right is weak, but has interesting structure full of branches. The next representation was so the next representation is multi-view reprojection. So another way of using these multi-view RGB data sets is through multi-view reprojection. It is a technique of illustration that is, this is the inverse of multi-view projection. So what you do is you take a 3D image and you capture multiple 2D images from different points of view. And then you apply, what you can do is once you have these different 2D projections of the same 3D object, you can apply, say, style transfer, and then reproject them back to obtain a newly rendered 3D image. Okay, so this is another project by thesis group last semester, which utilized this method in conjunction with a generative adversarial network. So in thesis, students basically explore and build a new design system to create the architecture of language. A specific GAN architecture called attentional generative adversarial networks allows attention-driven multi-stage refinement for fine-grained text-to-image generation. So if you provide this neural network with a set of sentences, it will try to convert them into an image. So an example of this is, you can see is here. So say in the first row, if you feed in the network with this text called a house, it tries to generate images that actualize this concept. Similarly, you add more details, keep on adding more details to this description, and the network tries to reconstruct, construct an interpretation of the sentences that you're providing. So what the students did was to use this architecture to generate views to use in the multi-view reprojection framework and to generate 3D models of language. They use these results to populate a city block with language-inspired buildings. Okay. This is, well, another use of multi-view reprojection where there are convolutional networks that are trained to perform classification on multiple views of the same object. So what you can do is basically, like I said, you can adapt style transfer optimization to on each of these different projected views, and then you can go back to reconstructing the full 3D object with these style transferred 2D images. Another useful representation for 3D objects is voxelization, where a voxel is basically an extension of a pixel to 3D space. So where in the case of pixel, you have a 2D grid of values. In this case, you have a 3D grid, which is basically, which signifies, say, if you look at the example, you can, if you see a chair, it basically signifies occupancy of a specific grid. So voxels are pretty easy to use because now all you need to do when incorporating into an existing machine learning architecture, all you need, the changes to the architecture aren't major, and it's pretty easy to extrapolate from networks which used to do, which process images to go on to process voxels. So there has been a huge amount of deep learning research that has utilized these voxels for 3D classification tasks, segmentation tasks, reconstruction, or even 3D object generation. So as you see on the slides, there are two examples. So the first example is something called 3D GAN, a 3D generative adversarial network. This is a 3D extension of a 2D generative adversarial network, which you can, if you remember from the previous workshop that Alexa talked about, is a framework for generating images from noise. So in theory, what you can do is train this generative adversarial network on a data set of 3D objects and attempt to generate novel ones with mixed styles by interpolating between these different representations that the network has learned. On the right-hand side is the other notable work. So on the right-hand side is basically a 3D modeling with generative adversarial networks that basically lets the user iteratively make edits to the voxel grid, and it refines the shape to approximate a real-world 3D object. So what you do is you first feed in user-defined 3D object. The network then goes on to iteratively produce a 3D object that uses the user-provided 3D model as base and tries to approximate a realistic 3D object. After that, what you can do is basically make edits to the the voxelized representation of this predicted 3D object to make changes and feed it back into the network so that, again, the network tries to approach a realistic 3D representation. While voxels are pretty simple to understand, the issue with it is it basically results in loss of low-level texture information. Voxels capture a high-level representation of the object pretty well, but if you need low-level information, you'll either have to increase the granularity of the voxel grid space, which results in increasing memory requirements, and also it results in high amount of computations, which is not, well, it's not feasible at this point. So moving on from voxels, you have the geometric forms. So a point cloud is, so point clouds have also been extensively used in 3D deep learning. Point clouds are basically simple and unified structures that avoid the irregularities which come with a regularized voxel, basically the increased memory and computation requirements, and are thus easier to learn from. Since a point cloud is just a set of points, it is invariant to the permutation of its members. And this basically requires us to ensure symmetricization in the network computation. However, a major downside to point clouds is, again, textures and lightning. Textures and lighting are difficult to apply because point clouds do not have surfaces, and local context of each. Also, another issue with point clouds is basically these are irregularly sampled, which means that large areas of empty space in the object representation can have a very small amount of points, and hence have a very bad representation of the overall 3D object. So the fact that these irregularities exist is bad for quantifying 3D style transfer between objects. There have been attempts made to perform deep learning with point clouds in an attempt to see what low-level information are being learned by these kernels, but it basically outputs garbage, which is to show that it learns representation that have no semantic value, effectively. So I forgot to change the slide deck. So these are voxels, which are basically regular 3D grids, and it is basically an extension of pixels onto a 3D space. But the issue with this is with an increasing granularity, there are issues with compute and memory requirements. And this is another presentation, which is point cloud. And while point clouds do not have the drawback of memory or compute requirements, they are irregular, and hence, as you can see in the case of this table, they can be difficult to extrapolate between two different point cloud representations of 3D models. Okay, moving on to meshes. So up till now, the representations that we have discussed all share one primary downside, that they do not have any sense of a connected surface. So, however, polygonal meshes, which basically consist of a set of vertices and surfaces, are promising because they are scalable and have surfaces. One advantage of polygon meshes over other representation in 3D understanding is compactness. For example, to represent a large triangle, all you need is a set of 3 vertices and 1 face, whereas voxels and point clouds require many sampling points over the surface. Because of this, polygon meshes represent 3D shapes with a very small amount of parameters, and they are very important for training deep learning models. Another advantage is that meshes are connected surfaces, which can be useful for defining 3D texture. For example, a local neighborhood of connected vertices and faces could define a 3D text doc. And there have been demonstrations which show that we can manipulate meshes to take on new shapes using deep learning, and examples of which are shown in the slide. So mesh is a 3D network which basically works on taking in a 2D image and an initial ellipsoid mesh, and it basically tries to project the information of the 2D image onto the mesh and iteratively deforms the mesh to predict the final 3D model. Due to the pros of these meshes, we're going to use meshes for the rest of the presentation and focus on how to operate on these meshes. So while that was a rather washed up presentation on different 3D representations, we are now going to focus on how to use these 3D representations and how can we do 2D to 3D neural style transfer. So the main tool that we use for 2D to 3D neural style transfer is something called a differentiable renderer. So a renderer basically, give me a second. Right, rendering basically refers to the formation of a realistic or stylized image from a description of 3D virtual objects. Similarly, a differentiable renderer is basically, it can be thought of as a very special type of camera. And it basically takes in color and vertices as input to produce pixels in an output image. But unlike a standard renderer, this whole process of taking color and vertices to render a final image is differentiable. So what it means is we can use this as a backbone function while we try to run it, approximately perform this operation by using a neural network. So given a surface model and a camera pose, if we try to render a predicted image and a depth for each pixel, along with, and what we can do is, now that we obtain, so okay, as we see in the slides, given a 3D mesh, what the render and would do is give us a 2D projection of this 3D mesh from a specific pose. And what we can do is we can use this 2D projection as a content image, and we can input also, and basically from this point onward, it goes back to how it works in a 2D to 2D style transfer, where we have a content image on one side and a style image which we want to put onto content image. And since this projection of the 3D object happened through a differentiable renderer, it basically, any final, once we do the style transfer onto 2D projection of the 3D object, we can render the 3D object back from this now altered and style transferred 2D image to obtain style transferred 3D mesh. So basically, changes in the pixel value of the 2D output image can get projected back onto the 3D vertices and texture by this neural renderer. Another use of this differentiable renderer would be changing the 3D structure of the 3D mesh itself. So given a 3D mesh, we can get a 2D projection of this mesh. And now, instead of changing the texture, what we can do is change this 2D projection into a different shape altogether. And once we change this shape and we feed it back to the neural renderer, it ends up changing the shape of the initial input mesh. And so, but the point is, this change only reflects back with respect to a specific pose. So if what you can do is, say, if you took a side projection of this turtle, and then you try to approximate it to a triangle. So it basically changes when you project it back. It basically affects only a small amount of vertices as we try to minimize the difference between the two projections. Okay, so going on to the experiments for this implementation of this 2D to 3D style transfer. Okay, so similar to how we performed a 2D to 2D style transfer, we need input 3D object and we need a style image. So for this experiment, I've already uploaded a couple of 3D models. So in our case, we will, for now, I'm only using this 3D object model of a dodecahedron. And what I'll try to do is try to project the style that is, say, contained in this image onto that 3D object. So again, from the start, for all you need, if you want to use your own 3D or 3D 2D style image, you need to create a Jupyter notebook. You can use any of the containers. Then you go on to choose a machine, which can either be a P4000 or P5000, and basically just set the time limit to however long you're planning to use. Usually, the only reason why we need a notebook is just for data upload. So an hour-long notebook is more than enough. And then you go on to, oh, I didn't choose a machine. Yeah. So, and then I basically just go on to create a notebook. So this would show that I requested a notebook and it is processing request. I already have a notebook running, so I can jump on to what we do once we do get assigned a notebook. So we open the notebook, and then within storage, you can upload 3D models in this 3D models folder. I would suggest that you use, yes, we need to start up a new notebook, or if you already have a pre-existing notebook that you haven't, that has stopped running, you can basically restart it. So yeah, I would suggest each of you make a folder under which you can upload your 3D objects that you want to experiment with. I uploaded my style images onto the style folder. You can upload any file using this upload button right up here, and basically select the file, open it, and when you click on upload, it'll basically upload the file onto this folder. I can see that already some of you have already made your own folders. I would suggest that others follow and make your own keep track of which files you're working on. All right, so once you have uploaded your input object and the style image that you want to use, you go back and now you go onto jobs. And you want to try use the job builder. You select your machine, which would either be a P4000 or P5000. In my case, I am selecting a P4000. Now, going on to select which container and workspace you're using. So if you refer back to the model zoo, the GitHub repository link that you were provided with, you can go down to the model zoo. And under here, the 5th, 6th, and 7th experiments basically pertain to the experiments we are running today. So for now, I'm just showing an example of 2D to 3D style transfer. So you click here. This gives you the link of the container that you want to use. So you copy this and paste this over here. It also defines what workspace you're using. So again, you copy this and paste this over here, right? Okay. Going on to the command. So we have a basic skeleton of a command that we want to use right here. And an example which basically fills in the gaps. So if you look at the command here, first two are again referring to what a script file that needs to run. So we don't need to make any changes to the first two arguments. And then there are experimental arguments that we can make changes to. So the first argument is basically the input object path. If you remember, we uploaded the 3D model into this folder right here. So the input object path, okay, I'll start filling it in the, okay. So the input object path is basically here in the notebook, it's under storage in 3D models and then the object file. So similarly, what you do here is you fill in storage slash 3D models, and then the name of the object file that you're using. All right. Okay. Then we go on to the next experimental parameter, which is the input to the path. Also keep in mind that there are spaces between each of these parameters, and please take care that you do not skip these, otherwise it will show errors. So the input 2D path is, again, we go to storage, and under styles, I uploaded 2D to 3D, say style.jpg. So it would be storage styles 2D 3D style to .jpg. Okay. So the parameter after that is basically this model, after running, generates a GIF of the model, viewing of the final output model object file, viewing it from different angles. So for now, I just put in test.gif, and then it asks us what the output directory is. So for now, you can either choose to store it in artifacts, which is again a memory storage associated with each job that you run, or you can basically change this and put this as storage, and this will store it. This will save the output file in the permanent storage folder right here. So if I do storage right now, it'll save the output right here. Okay. Okay. So that was the output directory. Now the final three parameters, experimental parameters, are the one that will have major effect on the output of this model. So last time we stuck to any value range between 0 to 100, just to show how much you can play, how much variance you can play with these parameters. I'm gonna put the style weight as 1 and the content weight as a very small value. So what this means is it's basically 2 into 10 raised to the power minus 9, and that basically gives you 9 orders of magnitude. It basically is they basically makes the ratio between the style and the content image as 10 to the power 9 to 1 effectively. And say I set the number of iterations as 300, and then I basically, you don't need to set the port or the custom metrics, and you basically submit the job. Right. this basically shows that the job that I just submitted has been queued up. So I already ran this experiment, and this will take some time. So running 300 iteration basically took me about 8 to 9 minutes. So I ran this experiment with, all right. So if I check the command for this, yeah, I will. Okay. Okay, so while I wait for this job to run through, and I can show you the results later, I'll go through the steps again. So you go to job builder, you choose your machine, which would either be a P4000 or 5000. So say I take P5000 for now. Your container and workspace are contained here within the deep design repository. The container, all you need to do is basically directly copy and paste the container and the workspace from the deep design model zoo. And then you go on to the command. So you can see the first two arguments of the command remain, don't need to change. All you need to do is make changes to the input 3D object path, the input 2D style image that you're trying to style transfer to, the output file name, which is basically the GIF that's being generated by the model as an output, the output directory, which can either be artifact or storage, depending on where you want to store the output of your model, the style weight, which can vary between 0 to infinity technically, but the point is the style and content beta are basically ratios. So depending on how you want to manipulate the final output, you can set this ratio to varying amounts. And the number of iteration is basically the number of times this model is going to run for to give a final refined result. So
again.
So okay, so it's the first two, then I chose a previous command which is not useful. My bad. 2D to 2D Styletransfer. So again, in bash, and this is the script file that we need to run. All you need to do is just copy paste this part. Then this is the path to the 3D object model that is stored in your storage space. So in my case, it's storage into 3D models into the file name. The next argument is basically the style image that you want to use. So this is stored in storage, styles, and say if I'm using 2D to 3D style, this is the style image that I want to transfer onto the 3D object that I'm generating. The next argument is basically the output file name, which you can name as anything dot, just make sure that you keep this file extension, which is dot graphical interface. So you can basically set it as a.gif or whatever you want to name your output file as. The next step is specifying the output directory, which is basically either you're setting it as /artifacts or you can set it as /storage. And the last three parameters are your experimental, the style weight, which I sent as 100, the content weight, which I set as 1, and the number of iterations that you need to run this model. And finally, all you need to is basically submit the job, and it will queue your job to be run in whenever a machine is available. So the previous job that I submitted it shows running now, and you can keep a track of the status by opening the log. So right now it's not showing the iterative log, and I can wait for it. It'll show up as soon as it is done downloading. But while we wait for the job to run, I can show you the results of a previously run job. So basically ran this job with the style weight set to 1 and the content weight set to 2 into 10 raised to the power minus 9. And I stored the output into artifacts. So when I click on artifacts over here, it'll show me the output GIF that was created. And it also stores the final 3D object as a .obj files, which contains a list of vertices and faces, and .mtl file, which is I think the texture file associated with this 3D object. It also saves the 2D projection of the 3D object that it uses during the differentiable rendering process. So if you want to see the output of what it looks like when I use the style weight as 1 and the content weight as 2 raised to the power minus 9. Give me a second. I'll open the file and share the screen. So, right. So it basically transfers the style of, I'll show you the style image as well. So I use this as the style image to imprint onto an empty dodecahedron 3D object file. And given the style weight as 1 and the content weight as a very small ratio, as in basically the style weight overpowering the content weight, this is what the final object looks like. Going back to the console. Also, please keep in mind that when you're copying over, say, this command to edit, please remove this returns to CD file transfer because it might basically result in errors. This might not exist within the artifacts directory, so it may result in a failed job. Also, it's still running. So, right. So as you can see, once it's done downloading the model, you can keep a track of how many iterations have passed since the model started running. So since I'm running for 300 iterations, it basically, for some reason, there's no line break with the iteration printing, but I think every 30% of progress or so, it starts on a new line. So you can keep a track of how many iterations have passed since the job started running. All right. So okay. So I'll take a look at your command. Okay. So first part's correct. There's an OBJ file, that's correct. The JPEG is fine. So you need to specify, if you go back and look at the commands, it's the object file name, the 2D path, and the output file name. So you missed, you skipped on filling in the output file name. So I would suggest, so after the object file name and the 2D image file name, you specify the output file name, and then the output path, and then the style weight, the content weight, and the number of iterations. And now if you rerun this job, it should run successfully. Okay, so the first job that I submitted has completed successfully. I go on to artifacts. Okay, so if remember, if you see this command right here, what I set was basically, I'll show again. So I set my output directory as storage. So if I go down here and check, I set my output directory as storage. So now my output isn't saved in artifact and with respect to the job, but rather if I go back to the Paperspace console, and I can see that it saved the output file as storage right here. So if you would like to save your outputs permanently, I would suggest making your own folders and giving that path. So it would be like, so I would go here to new. I set up a new folder. Right, so it created an untitled folder. I can rename this folder by, you can select it here and you can rename this folder to say outputs, or basically I set it as under my name. And then when I run the previous command again, all I need to do is basically rerun. And I set it as /storage/ the folder name that I just said. And now it will store the output under this directory. So going back, this is the output of the result that I just ran. And I can select this and download it to my local system. And I can view what the output looks like. Or I think you can directly access it too. Yeah, if you directly click on the file, it should show you what the output GIF looks like. Okay, so right, so that's how you run the 3D style transfer, and you can try run it on your own personalized 3D object files as style images. And like Matthias suggested, I would recommend that you try manipulating the style weights and the content weights to have extreme variance in the ratios and see how it affects your final output that you're generating. And the number of iterations is independent of the style and the content weight, but it helps give a refined result when you run it for longer iterations. Parallelly, there are other 2D to 3D experiments that you can run, which use the same concept of a differentiable renderer, but result in a different output. So this is an experiment where you're running 2D to 3D deep dreaming. So what it does is basically, given a 3D object, deep dreaming is basically a tool for network visualization. So what it does is basically, if you train a full neural network to, say, classify images on a specific data set, and now what you do is basically take this fully trained neural network and and okay, I've been asked how to name the output file and the output directories. So okay, so if I to show again how to change your output file name and the output directory. My system crashed. Okay, it's running again. I do rerun. You look at the command again. So if you refer back to the skeleton command, it's the first two are the script file and script files. The third parameter is the 3D object. The path to the 3D object that you're using. The next is the path to the 2D style image that you're using. And this here is the fourth, the first, second, third, fourth, fifth parameter is the output file name. So the only thing that you need to ensure is that the file extension, .gif, is mentioned with the output file name. And you can set the output file name to be anything. So in my case, I had set to test. You can simply set it to style.gif, and it'll save the final output as style. The result that I showed you as style.gif. And as for the output directory, you have two options. You can either set it as /artifacts, which basically results in the creation of a job-specific memory where the outputs are stored, and you can access this directly from after the completion of the job from the job under the job description, which I will show you. Or you can set it as store the output in your permanent storage, which is .storage, and this would save the final output right here under storage. But since in the interest of reducing clutter, I would suggest that everyone should basically, make a folder where you can, under your own name, and then all you need to do is basically mention storage / the folder name that you just created. So in my case, it is Manus, and this is where you will find the output of your experiment. Okay. And in the case that you are saving it to artifact, it will basically store the final output right here. You can download this using this button right here. So in the case of, so this is an example where I was, okay. So if I look at the job parameters for this job, I ran it with a style weight of 100 and a content weight of 1, and I ran it for 300 iterations. And we can look at what the output looks like. This is the wrong job. So I can download this right here to my local system. If I open it, and share this. So this is again the stylized 2D to 3D style transfer, where the style weight is now 100 and the content weight is 1. And like Matthias suggested, I would again urge you to try different weight settings, see how it affects your output. Screen. Okay. So the other experiments that you can run are, well, one would be the vertex optimization, which was basically the final slide I showed you, which were basically given a 3D mesh and you project, get its 2D projection, and now you try to basically change the shape of the 3D mesh itself instead of just the texture. And that, again, all you need is the first two parameters right here remain the same. The input object file is again so in my case. Okay, and if you need, again, to show that you can rename these folders, just click on this check mark right here and you can rename it and you can set it to whatever name you feel like. But as a general rule of thumb, I would suggest that you only store results that you would need at a future point in time. Otherwise, artifact is a perfectly fine storage space, since it handles job specific. If you're just experimenting with how the output should look like and you don't need that output at a future point, I would suggest that you use artifact, since it only exists while the job exists, and once you delete the job, the memory is freed up. Right, so say in this case of 2D to 3D vertex optimization, the container and the workspace links are mentioned right here. And moving on to the command format, the first two remain the same. The input object path would be similar to what you use for 2D to 3D style transfer, which was which is basically, let's start a new job effectively. So I go into selecting a machine, 5000, container image. No, you do not need the notebook running the whole duration that you're sending jobs. The only requirement of the notebooks is to basically facilitate in data transfer. So once you're done uploading or downloading from the storage, or you can put down the notebook, and you wouldn't you won't need to use it, basically. So in this case, if I can basically go back to the notebooks and I can stop running, since I do not need to run the yeah, since just leaving a notebook running while you do not have any use for it is basically effectively an inefficient way of inefficient monetarily, effectively. Yes, it would keep charging money while you aren't using it for anything. So this basically save the state of my notebook, and I can restart it at a later point, and I don't need to start up a new notebook, since it basically saved the configuration that I'm using this paper space was fast AI container, and I'm running it on a P5000 machine. And again, if I need it, I can basically just start it up right here and then open it up, and I can upload the data that I need. And once I'm done uploading or downloading the data, I can stop it and save it for a later point in time. So for the other experiments that you can try running is the vertex optimization, where basically I try the job builder. Again, I choose a machine. I copy over the container and the workspace from the model zoo. And now I go on to editing the command that I need to run. So again, as with almost all experiments, the first two you can directly copy and paste here. and then it goes on the experiment parameters that we do need to edit on our own. So for the Obj path, it's basically the same 3D model that I'm using. So storage 3D models. BJ. The 2D input path is the command line case sensitive? Yes, indeed it is. So you would need to make sure that you match the case when you're running it. So should I change this to small m? This would, since it would say that this directory does not exist because there is no folder under storage which is 3D small m models. Say you set the input 2D path as so in this case, the input 2D path that you're putting in is not a style image, but rather a shape modification image. So it would be something like a mask. So if you remember from the presentation, right. So if you see from the presentation here, this is basically the mask to which you want to change this 2D projection. You want to change the shape of this 2D projection to the other 2D ground truth projection. So it's not a style that you're transferring, but rather the shape that you want it to affect, right? So I don't really have a mask image saved right now, so I can simply just, or actually, so if I, give a second, yeah, that does not work. So if I need to restart, it'll again ask me. I just set the time limit to 1 hour because I don't really need it for long. It requests. Is the mask just an alpha channel? I will get back on that. I can check whether it's just an alpha channel that I need, or does having an RGB 3-channel RGB image affect the final vertex optimization. I'll check it and get back to you on that. So I requested it. It's getting provisioned. Right. While I'm waiting for the notebook to get started up, another 2D to 3D experiment that you run is the 3D deep dreaming. In this case, there is, if you look at the command information, there is no input 2D style image. So all you need to do is basically feed in the 3D object model and the output file name and the path that you want it. The last two parameters are different from the style transfer. In this case, you're providing image size, which is the size of the final. This is okay. It's not the final, but internally it uses this image size and has a to do the deep dreaming process. So you can set this again between anywhere between 128 to 1536 is what Matthias mentioned during the last workshop. And the number of iterations is again the number of times you want this model to refine the final output over. And all you need to do is basically submit this command onto the job interface, and this will give you interesting results. You should try it, and you'll see what happens. Just for the 3D object. So I think it's the style format that matters. So till the moment, I think the format for a 3D object model, if I just Okay, what happens if I open this?
And maybe a quick comment about that question of the 3D models. So they have to be OBJs, they have to be watertight, I would say. And what we figured out is that they obviously work a little bit better if they're quadruples and not triangles. Also, the resolution of this image of this models is very important. So do not, I mean, super high resolution models, I wouldn't use those because just it won't compute because it's too complex. Yeah. So you have to take care that the resolution of your model is not overly large. I think one resolution we discussed last year was about 10,000 faces maximum. It seems it can be more than that, but certainly not like 500,000 or 1,000,000 faces. So let's say if you try somewhere between, you can start with one model with 10,000 faces and then slowly go up and see how high you can go before it crashes.
All right, so again, this is, yeah, so I think what I 3D objects saved under the OBJ file extension should work. All right, so if I were to go to storage, look at styles, and I think there was something called lines vertical, right? And this is basically, yeah, it's basically a mask. Say if I use this as a mask image, so I do storage styles slash line vertical.png. All right, and so I put in the 3D object file path, the 2D mask path, the output file name. So let's do again test.gif. The output directory. So say I want to store this to artifacts, and the last part is a number of iterations. So say I run it for 300 iterations. So if you look at the full command again, the first two you can directly copy over from the model soup. Then cross-checking, the first thing is the OBJ file. This is the OBJ file. The second, the parameter after that is the input 2D mask file. So I'm just using lines vertical, which is already present. The output file name, which is just the GIF file that I mentioned here, and the output directory, which is artifacts here, and the number of iterations. And I basically submit the job. And it used the job I got. Okay. So similarly, you can do a similar setup for 2D to 3D neural renderer for 3D deep reading. The only difference is you do not need a style image in this case. And your final parameters change from style weight, content weight, number of iterations to just image size and number of iterations. Yeah, I can help troubleshoot if someone is having issues running the 2D to 3D style transfer experiment. Please feel free to reach out. And I apologize for the botched up presentation. I had, yeah, Zoom does not allow me to use presenter view while I'm sharing my screen, so I had to keep swapping between windows, and hence I ran out of sync.
That's no problem, Manas. I'm just saying, so we have about 10 minutes to go for today. Yeah. So are you finished?
Yeah. So there are the 3 experiments which are related to 2D to 3D style transfer as such, and I can help others. If someone is running into issues running these experiments, they can ask me. Or otherwise, I'm always on Slack, and you can message me there too if you're running into trouble.
Sounds excellent. Thank you very much, Manas. This was a great presentation. I recorded everything. I'm going to try to cut it up as fast as possible and put it up again on the YouTube channel so that you can repeat it if you want to. I know it was a bit fast, but if you can rerun it, then it becomes, I think, more accessible. And also the code, I think it becomes a little bit more clear once you have looked into it maybe another time, how to set up the code correctly. It's just about understanding the logic, and then you can change things inside the code. So Mana, thanks a lot. Highly appreciate it. Looking forward to see you next week again. And are there any questions from anyone? Yes, I already asked Manas. We're gonna share also the slides. Yes. Manas, that's right, right?
I will share the slides. I can send them to you, and you can share it with class.
Okay, I'll do that. Okay, any other questions so far?
Can you clarify stuff for next week? I was reading that there's going to be a discussion and there are some movies and stuff you listed on the handout.
Yes, I was just about to say something about that. Thanks a lot. So basically speaking, let me just quickly check again. Before I look it up, just read it to me and we discuss it while you read it to me, what the task is for next week.
All right, so it says next week, September 25th, I will give a lecture. Following the lecture, please think about points that may be connected to the assigned readings. How would you create an argument for or against to present artistic content or concepts? And then you list a couple movies and there's like 3 things under a music list.
Yes. So basically, there's again 2 parts to the session next week. So the first part of the session is again 1.5 hours, yeah, which is going to be about 40 minutes, a lecture that I do about art and AI, yeah. And then after that, we have a roundtable discussion between all the students and myself about what you just saw, yeah, like the lecture. And basically what I want to have from you guys is you have to watch this lecture very carefully and build up basically arguments either for or against the content that I'm presenting. Like, do you agree? Does AI have creativity? Does it not have creativity? Does it have agency? Does it not have agency? Yeah. Does it create a new sensibility, or am I imagining it? Yeah. These are important. These are really interesting questions because it's exactly because all of what I'm gonna say next week. Let me put it this way: every time I say art in my lecture next week, you can replace that in your mind with architect or architecture, because I think it accounts for both areas. I'm just showing you examples from the arts because there is much more out there right now than there is about architecture. So I cannot show you that many examples. Yeah, I showed you already some, but in specifically that conversation where it becomes not just a tool of expediency, but really one that questions very specific philosophical questions, ontological questions, and epistemological questions. That's why we need to discuss this through the examples of the arts. But basically, it's transferable to architecture. So, and then the roundtable is the discussion around that. It's a very new area of interrogation, both in terms of architecture and art, but also philosophy. So it's uncharted territory we're entering, and I will give you some examples. And the movies and the sound, these are there for you to watch next to doing your exercise for next week. Yeah, and the exercise for next week, or the homework, is to create a series of 2D to 3D style transfers. Yeah. And you saw it today that we used Manas used a rather simple geometrical body, an OBJ, yeah. and then basically an image from nature that he style transferred onto that 3D model. Yeah. You have to do the same. Yeah. But I would like you to make a family. So a family means 5 objects minimum. I would 3, no 5. Let's say 5. Yeah, 5 objects where you're using that style transfer technique. And I want you to do 2 with examples from nature, like any sort of, by the way, textures, close-ups of natural things work really well. Let me quickly share with you a Pinterest board that I have on that. Give me a second here. Where is my boards? Okay, I'm gonna send it to you in a message in a minute. Anyways, you can see some of those patterns where I'm there. And the geometric bodies, it's something you can do. You can do, for example, in Rhino. Yeah, just do like not necessarily a cube. Yeah, but a tetrahedron, a hendecahedron, some sort of polyhedron. Yeah, so not just a cube. You saw that today we used a dodecahedron, yeah, as example. I like to play with the, like, I squish them sometimes, it looks a little bit better, but it's up to you how you do it. And then, so 2 with natural patterns, 2 with patterns from architecture history. With pattern, I don't mean like really a pattern, but what I mean by that is, for example, a nice close-up photograph of a Gothic cathedral facade or something like this, yeah, or from a Baroque church, just a ceiling. We saw some examples today already, yeah. But be really more careful with what kind of piece you take out to do that transfer, yeah. It seems that flat views work quite well, so not like completely perspectival with a lot of environment, rather really like cutouts of parts look really better, yeah. Does that sound clear? Yes. Yes. So again, I'm going. Yes, please.
Just one question. So the 3D object that we make should be some symmetrical geometric form versus like a 3D like polygon model of like an animal, for example, right?
I wouldn't do anything too complex, because the first exercise is there for you to understand what's happening in the process. So if it becomes too complex, it's too difficult to recognize what's happening. If it's a simpler object, it's easier.
Okay.
But think of it as a chunk. Yeah, it's a chunk that you're playing with, and that will give you a better understanding of what the process is doing. Okay. Awesome. Any other questions?
I think we're at 4 in the family right now.
4. 1 is a freebie, whatever you like. Does it sound fair? All right, sounds good. All right, so it's exactly 4 p.m. Thanks a lot, everybody. You know, you can reach me on Slack anytime if you have any questions. Yeah, I think that's pretty much it, except is there still any questions left from anyone? All right, so I'm going to share the slides. I'm going to send you the Pinterest board, and oh yes, and the Miro board invitation. That's also what you need. Okay.
Okay, so I do have one quick question.
Yes,
so you said for the styles, we want 2 examples from nature, and then what were the other ones?
2 examples from architecture history.
Architecture history. Okay, thank you.
Great. I think that what is there another question somewhere? Doesn't look like that. Okay. So Manas, thanks a lot again for the workshop today. It was amazing. And that's it for this time. So thanks a lot, guys. See you next week. Bye, guys.